Second. Okay, so in the last class, I believe we had covered a couple of cryptographic algorithms. We started with Wigner-Wurman cipher. We also covered Caesar cipher. And in terms of the block cipher technique, I remember we did discuss Playfair cipher technique. And if you remember, Caesar cipher was just plain text plus the key mod 26. And in order to decrypt it back, it was ciphertext minus the key mod 26. In terms of Wigner cipher, you create this kind of a matrix where you have um, this overall, all the alphabets arranged in the rows and columns format, where the row is considered as the plain text and the column is considered as the key, and then you encrypt and decrypt it using looking for specific locations. There was another formula that you can use for Wigner cipher. It was pi plus ki mod 26 for getting the ciphertext, and in order to get it back, it was ciphertext minus the key mod 26. The Varman cipher was also considered as one-time pad, and we did discuss it was you add the two alphabets, and if it was greater than 26, you will subtract 26 from it. And if it is, in order to decrypt it back, you were checking if the sum was less than zero. Then if it is less than zero, you add 26 to it. So that was Varman cipher. In Playfair cipher technique, you create a matrix which is 5 cross 5 matrix where initial alphabets are arranged in the form of the key that you use, and then you write all the unique alphabets, but I and J always take the same alphabet. And we did discuss about that technique. There were certain rules in terms of when they are in the same row, or when the plain text is in the same row versus when it is in the different row. So we did discuss, but I think it was clear. In this class, I will start with the Hill cipher technique. Hill cipher technique is another important cryptographic algorithm, and it takes into consideration matrix multiplication. So the way this specific Hill cipher technique works is, so far in the previous example, what you were doing were, it was plain text plus key mod 26, or plain text. It was all addition and subtraction. However, in block cipher technique, the only difference is that you multiply your key times the plain text and mod 26, and you arrange and you create, and it's a block cipher technique because you take two alphabets together. To help you understand, or let me get back to this slide. um, there are three different kinds of symmetric key algorithm. One is considered as monoalphabetic, where you take a single character and and you add some other character in order to get the ciphertext. Polyalphabetic is where the keys and the plain text could be different. That is the reason it is considered as poly, which means, if you let me show you this slide. This is polyalphabetic because the plain text that you are encrypting could have key which is different in the first iteration versus in the second iteration. So that is the reason it is considered as polyalphabetic. Monoalphabetic is when you have the key always fixed, which is +3. Caesar cipher was an example of monoalphabetic cryptographic algorithm. In Wigner and Wurman, the plain text that you are encrypting can have key different in the first round versus in the second round. And that is the reason it is termed as polyalphabetic. There are these two different techniques, which is Playfair cipher and Hill cipher. They come under block cipher technique because you process in the form of block. You take two characters together. And if you remember, in the Playfair cipher technique, you were taking two alphabets together because you were, if you had to encrypt instruments, you were taking IN, then ST, then RUMENTSC. It's a block. It's not a single character. It's a block of character, two characters together. That is the reason it is considered as a block cipher technique. Hill cipher is also a kind of block cipher technique where you process the characters in blocks, like two characters, three characters, and the larger the character set you do, the encryption and the decryption algorithm becomes more complex, and we will understand how exactly. But before that, I'll go step by step so that you understand. So I'll open my um, whiteboard. One second. And I'll try to explain in details because your lab 4 is also based on that. One second, laser pointer red. Let me see how exactly this will work. But so let's start with the Hill cipher. Hill cipher technique is also a kind of block cipher technique where you process characters in blocks together. So first of all, let me just write down all the characters and the numbers associated with each one of them. M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. So you start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So you have these arrangement, and let us suppose that you want to encrypt a plain text, which in this case is your help. So plain text is help. So the way that you process these characters is that you take two characters together. So we are currently doing 2 cross 2 matrix multiplication. But if this particular algorithm can be further generalized in processing 3 characters together, 4 characters together, 5 characters together. But in this example, I will cover 2 characters together. HE will be processed together, and then LP would be processed together. So the very first one is that let us imagine the key that you have is DDCS, which means you will arrange this in the form of a 2 cross 2 matrix because you are processing 2 characters together. So here in this case, D corresponds to 3, another D corresponds to 3, C corresponds to 2, and F corresponds to 5. So your matrix, which you have created because you're processing 2 characters together, is 2 cross 2 matrix. Then what I will do is I will take my first 2 alphabets, which I want to process, which in this case is H, E. So H corresponds to 7 and E corresponds to 4. As I mentioned, here in a Hill cipher technique, the cipher text is key times, and this is times, plain text mod 26. You have to multiply. So you will take the key and you will also take your plain text. You will multiply them together to get your ciphertext. So your key is 3, 3, 2, 5, and your 2 characters that you are taking is 7, 4. So this is a 2 cross 2 matrix. This is a 2 cross 1 matrix. So the resultant would be a 2 cross 1 matrix. I believe everyone knows how to do matrix multiplication. For those of you who don't know, I will do it in case if you want to just brush up your memory in terms of solving it. So you take your first, you do row times the column, then row 2 times the column. So here in this case, it would be 3 times 7 plus 3 times 4. That would be your first element. The second would be 2 times 7 plus 5 times 4. and this is mod 26. So if you will solve this, the first element would be 33 and the second element would be 34, mod 26. And everyone knows 33 mod 26 would be the remainder value is 7, and 34 mod 26, the remainder value is 8. So 7 and 8 corresponds to H and 8 corresponds to our I. So the ciphertext related to HE is, so this is your plain text and your ciphertext that you get is HE. So this is your ciphertext. This is your plain text. Any questions so far? Is everyone following up? Okay. Um, that is your if you have to get from your plain text to your cipher ciphertext from your plain text. Now, in order for you to decrypt it back, the formula associated with that specific technique is so your ciphertext is key times your plain text mod 26, and in order to get your plain text back from the ciphertext, it is k inverse times your ciphertext mod 26. So you have to calculate k inverse in order to and multiply with the ciphertext in order to get back your plain text. And I will solve it for this specific example, which is HI is the ciphertext. So I should get HE as my plain text back again. And if it is right, then it means the calculation that we have done is right. Does anyone know how to calculate K inverse? If you have a key uh, and a matrix which is 3, 3, 2, 5. Does anyone know how I can calculate K inverse out of that?
Isn't it like when you switch A and D and then you make B and C negative?
Yeah, you do three operations in order to get this K inverse. And generally, K inverse is 1 over your determinant value of your K um, times the adjugate for K. That's K inverse. And I'll tell you how do you calculate the adjugate as well as how do you calculate the determinant value for a metric. So let me get rid of all of this. Okay, so we have this key which is 3325. So in order to calculate the adjugate for K, you have to do three operations. The first operation is uh, transpose. The second operation is find the minor. And the third operation is finding the cofactor. So if you have a matrix which is A, B, C, D, which is this key value, which is 3325, the first step is that you calculate the transpose of this specific matrix. So transpose is that you just switch the diagonal elements. So A, B would remain same, but C will come over here and B will come over here. So that is transpose of a 2 cross 2 matrix. In order to calculate the minor of this specific matrix is that, this is D, A, C, B, D. In order to calculate the minor, what you do is you hide. I wish I was in person, I could have shown you. But the way you do is for the first element, for this element, you will hide, let me make it in different color. You will hide this and this. So the resultant is D. If you have to get the second element, you will hide this and this. So the resultant is B. In order to calculate the third element, you will hide the row and the column associated with that element. The resultant would be C. And in order to calculate the fourth element, you will hide this and this, you will get an A. So whatever element you want to you want to find the value, you will hide that row and specific column in order to get the um, output. So you get the minor. And the last factor is a cofactor, which assigns negative values to certain coordinates where the negative values are assigned in terms of -1 I plus j, where I and j is the row and the column number. So what it means is that if this is element, so this is 0, 0, 1, and this is 1. So I and j is -1, 0 plus 0, which is -1 to the power of 0. What exactly is that? Is that a positive value or is that a negative value?
Positive?
Yeah, positive value. So this element would remain as is. So D would remain as is. The next element, which is -1 I plus j, would be 0 plus 1, which means that it would be -1 to the power of 1, which is negative. So this second element will become -b. The third one is also -1, 1 plus 0. So it is -1 to the power of 1. This would be -1 again. So this element would be -c. And the last one, which is -1 to the power of 1 plus 1, this would be 2, which is positive value. So D minus B minus C and A. So this would be the adjugate for the key. Gala or Dino, what exactly is that SMH? I don't know. What is SMH?
It means shaking my hair or head, I guess. It's because I misspelled positive.
Okay. Okay. So here, this educate is basically calculating the resultant value is this final value that you are getting. So for this specific key, which is 3325, what we have to do is first calculate the educate. So the very first step is calculating the transpose of this specific matrix. So this is 3325. It would be 3, 2, 3, 5. The next one would be to calculate the minor. So the first element would be 5. The second element would be you hide this and then this. So you will get a 3. In the next, you will get a 2. And in the last, you will get a 3. And in the last, you just assign the value. So this would be 5, -3, -2, and 3. So this you are getting as the educate of the key K, which is 3325. Now, in order to calculate the determinant value is you multiply the diagonal elements, so which is 15 minus your 6, which is 9. So what you will do in the end is, the resultant of this is 1 over 9 times your 5 minus 3 minus 2, 3 mod 26. Does anyone know how we will solve this? It's 1 over 9, 5 minus 3 minus 2, 3. I think this part you can solve because it's just 5 mod 26, negative 3 mod 26, negative 2 mod 26, 3 mod 26. This part is easy. But what about 1 over 9? Any guesses? This is a division. And what did I speak in the class with respect to whenever it is a division operation? How exactly you can compute that specific value? Then anyone recall? Remember this term inverse? Can we calculate the inverse of this specific number so that this value can be computed, which means what I should multiply with 9 under mod 26, which will give me the resultant value as 1. Can anyone tell me what would be that value? What I should multiply with 9 so that under mod 26 would give me
3.
3. Yes. So 9 times 3 mod 26 would give me 1. So this value, which is 1 over 9, can be written as 3 times 5, negative 3, negative 2, 3 mod 26. Is everyone following? Is it making sense? What exactly is happened over here? Any questions?
Can you maybe go over that one more time? Just the last part there where you yeah, where you
Yeah.
got just
So,
the root for it.
mhm. So if you remember, when we were discussing that whenever we are doing any kind of mod operation, so for instance, if we do a plus b mod 26, that is a mod 26 plus b mod 26, uh, and the whole resultant mod 26. If it is a minus b mod 26, that is also okay, which is a mod 26 negative minus b mod 26 mod 26. And whenever it is multiplication, that is was also okay, which was a mod 26 times b mod 26 and the whole resultant again mod 26. But when it is division operation, a divide by b uh, mod 26, this specific value, which is a by b, is considered as a b inverse mod 26, which is how exactly this value, which is what we are calculating, inverse of 9, because this is 1 over 9, which is a division operation, which means that I want to calculate the multiplicative inverse for this value so that the resultant would be equal to 1, because that is what I am getting, 1 over 9. So what I should multiply with 9 so that the under mod 26, that the resultant would be 1. Let me show, I think I might be having the slide as well. If you remember this part that we covered, this part, modular inverse. It's in one of the previous slide decks, which we discussed, that how do you calculate the modular inverse? And modular inverse is A times A inverse is congruent to 1 mod C, which means A times A inverse mod C should give you the value as 1, which is uh, circling back to the group concept, that what I should multiply with a specific number, that it will lead to the identity element. So since it's multiplication operation, the identity element is 1. And that is the reason what I should multiply with A, which in this case is 9, so that under mod 26, that it will give you the resultant value, which is 1. So in this case, since we are solving, where exactly is my cursor? One sec. So in this case, um, what we are doing is we have to solve 1 over 9. So this can be written as 9 inverse, which means that what I should multiply with 9 such that under mod 26 that it will give me the remainder value as 1. And in order to calculate the multiplicative inverse of a specific number, we did cover your extended Euclidean algorithm. Remember extended Euclidean algorithm to calculate the multiplicative inverse. Any numbers when you divide um, under this something, first you calculate the GCD of those two specific number, and when you extend it, the GCD of two numbers can be represented as AX plus BY, where this X and this Y we were calculating using the extended Euclidean algorithm, and that value, if it was equal to 1, um, this value was considered as the multiplicative inverse of A under whatever we are doing in terms of the mod operation. Does it make sense, or is it too much? Is it making sense what exactly I'm covering? Is it why are we doing this?
Yes, ma'am. That was perfect. Thank you.
Okay, so 1 over 9 could be solved as 3 times 5, negative 3, negative 2, 3, mod 26. And we did this because it is a division operation. So which means that I have to calculate the multiplicative inverse of 9. And in order to calculate the multiplicative inverse of 9, it means what I should multiply with 9 under mod 26 operation in such a way that the resultant would be equal to 1, which in this case becomes 3. So if I will solve this, this would be 3 times 5, which is 15, 3 times 3, which is negative 9, and then 3 times 2, negative 6, and 3 times 3, 9, mod 26. So 15 mod 26 is 15. What would be this value? Negative 9 mod 26. Can anyone tell me what would be that value? Negative 9 mod 26. Does anyone remember? How do you calculate negative mod, the resultant of a negative value under mod operation? You take 26 minus 9 mod 26, which in this case is your 17. Perfect. So this would be 17. Negative 6 mod 26 would be, once again, 26 minus 6 mod 26. The value would be 20. And this is 9 mod 26. So we just calculated this part, K inverse. What we are still left is multiplying it with the ciphertext under mod 26 in order to get the plain text. So this is our key that we have, K inverse that we got. So our plain text is K inverse, which is 15, 20, 17, 9 times our ciphertext, which the ciphertext was HI, if you remember HI that we solved, which was 7, 8. H is corresponds to our 7 and I corresponds to 8, you will multiply this together. So this would be 15 times 7 plus 17 times 8. This value would be 241, and 20 times 7 plus 9 times 8 would be 212 mod 26. If you will further solve this, this will be 241 mod 26, which would be 7, and 212 mod 26, which would be 4, which is 7 and 4 under mod 26. And 7 corresponds to H and 4 corresponds to our E. So H, E. So we are able to get back our plain text from the ciphertext that we computed using all this calculation, which we just did. Any questions? So we are able to get the plain text back doing, first we are calculating the K inverse, and then we are calculating, we are multiplying it with the ciphertext. And then under mod 26, if we will do, and if we get back the resultant, then it means that we did our encryption and decryption algorithm fine. And it's a 2x2 matrix. Imagine doing it for 3x3, doing it for 4x4 matrix. And the larger you process the blocks together, the complex the algorithm becomes, and it is much preferably used if you are if you have to encrypt an algorithm or a plain text and you want to make your algorithm much complex. People do prefer to use like much larger blocks size processing rather than just taking two blocks together. And the example that I covered is with respect to 2 blocks of solving. Let me get back once again. So all this example that I just showcased to you, I have depicted in this slide where I have solved this and getting back to this number itself. One more thing I wanted you guys to always remember, and sometimes students do get confused, and which is very important. And I'll tell you what exactly is that part. Let me open my whiteboard once again. Okay, so question for each and every one. This is with respect to when you are doing some kind of calculation, like determinant value. So as I mentioned, your K inverse is 1 over your determinant value of K times educate for the key. So when, for instance, if you have a matrix something like this, 2, 2, and 3, 3. Can anyone tell me what would be the determinant value of this? Yeah, so 4 minus 9, which is negative 5. It should be negative 5. It is not 5. So do not get confused when I am writing this symbol as a mod of a specific value. So this is negative 5. It is not positive 5. Do not make it to plus 5. It would be negative 5 mod 26. And you can solve this once again using 26 minus 5 mod 26, which is 26 minus 5, which is 21. So it would be 21 in general with respect to 1 over 21 rather than, and that would be what I should multiply with 21 under mod 26, which will give me 1 value. Okay. It should not be considered as your once again, it should not be, do not make it as a positive value just because it's the symbol is written as this under this um, slashes, which means make it saying that it is an absolute value. It is not an absolute value. It is the same value which you get by multiplying the diagonal elements together, which is 2 times 2 minus 3 times 3, which is tending to be negative 5, which means negative 5 mod 26 you have to do in order to compute the value, which is 1 over 21. So what I should multiply with 21 in order to get this specific value. Sometimes students do get confused and they just do 1 over 5. This is incorrect because it's negative 5. It will not be considered as a positive 5 value. So always remember that. Do not make that specific mistake. But any questions so far with Hill cipher technique? No questions? Should I go ahead then? If 2 cross 2 matrix is everyone able to understand? Okay. So this is another illustration for a 3 cross 3 matrix. In the exam, I will not be giving you a 3 cross 3 matrix, but you should just know that we solved it for 2 cross 2 matrix, but the same can be generalized for a 3 cross 3 matrix. So here, if you will see the very, since we are processing three words together, three characters together, so we will take ATT together. So ATT is the one word that we will process together because it's a 3 cross 3 matrix. There is this key which is DKUUJRJER. So you will create, you will write the corresponding numbers for each of these alphabets. So you will get a 3 cross 3 matrix. Your ATT would also be converted into a specific matrix, which is 0, 19, and 19 because it's ATT. It's the corresponding characters for A, the corresponding character for T, and the T. So it is 0, 19, 19, and your key. So you will multiply this time 0 times your 3 plus 19 times your 20 plus 19 times your 9. So this is row versus column multiplication. In the previous example, I was doing um, this row versus this column. I have just slightly tweaked it so that you understand how exactly the calculation is done over here. So which in this case is row, column, row, column, once again, row, column. So this will give you three values, which is 5, 13, and 22 under mod 26 operation. So your resultant cipher text is F, N, and W. Once again, this is row versus column multiplication. So you will get, so uh, this is 1 cross 3 matrix, and this is 3 cross 3 matrix. So the resultant would be 1 cross 3 matrix. Which in this case is 5, 13, and 22. One, your only one row, which is 5, 13, and 22. Now, in order to calculate K inverse and then followed by your multiplying it with the ciphertext, the similar kind of technique you would do. Here, the determinant value is for a 3 cross 3 matrix. So here in this case, the determinant value would be taking the first element and multiplying the diagonal elements, which is 9 times 17 minus 4 times 17, then negative, then take the second one and hide this part and do 20 times 17 minus 17 times 9. So you will get the second value plus, then you will take this element 20 and then you will multiply 20 times 4 minus 9 times 9. So in the end, you are getting negative 23 mod 26. So you will convert this negative 3 mod 26 to its positive value, which is 26 minus 23 mod 26, which is equal to 3. Once again, this is 3. So 1 over 3. So what I should multiply with 3 under mod 26 operation, that it will give you a 1. So we just saw that 3 multiplied by 9 under mod 26 will give me 1. So 1 over 3 can be written as 9. And that is what we are doing over here as well, which is this 9 times the educate for the key K that we are solving. And once again, for finding the educate, you have to first calculate the transpose, then you have to calculate the minor, and then you have to calculate the cofactor. Once again, the same process repeats. The very first step is that you transpose the values where the row becomes the column. So 3, 20, and 9 is the column which will become a row, 3, 29. The second row which is 10, 9, second column which is 10, 9, and 4 will become the row which is 10, 9, and 4. And the last column which is 20, 17, and 17 will become the row which is 20, 17, and 17. So this becomes the transpose. You calculate the minor. Once again, in order to calculate the minor value, you hide that element. So for getting the first one, you will hide the row and that respective column and multiply. So 9 times 17 minus 4 times 17, which would give you 85. And all this is solved over here. So you will get the minor very similar to 2 cross 2 matrix. But here you have to solve those small matrix. And the last step is finding the cofactor, where you assign the negative value using negative 1 over I plus j, and where I and j are the row and the column values, which in this case would be positive, negative, positive, negative, positive, negative, positive, negative, and positive. You will assign from the previous resultant key value, you will assign the value, you will get something like this. So you will multiply it with the determinant value under mod 26 operation. You will get the resultant like this. You will multiply your cipher text that you got in the previous round times your key, which you have solved. And this would give you something like this. And you are getting your final plain text back again, which is ATT. I know this is a little bit complex, but once again, I'll not be giving you a 3 cross 3 matrix. You should just know 2 cross 2 matrix, and this you have to code this in your lab number 4. Okay. Any questions? Was it too much, this algorithm, or it is okay? Sorry, I can't see you guys. I do not know if you are understanding or if I'm just talking to myself.
No, we're here.
Yeah, we're here. It makes sense. Thank you.
Okay, so I will be just giving you 2 cross 2 matrix, and you, for your lab number 4, you have to solve this. You have to process 2 characters together and then you have to communicate. And that is the reason you need to understand the basic math behind how to solve a 2 cross 2 matrix. Process 2 characters, do this matrix multiplication in order to get the ciphertext and your plain text back. But you should remember how to calculate, how to do simple matrix multiplication. Row times column, you should know. And the second one is that you should know how to calculate the educate for key and how to get the determinant value. And 1 over any value should be what I should multiply with that specific number to get under mod 26 that it would give you a 1. That would be that specific value that you will replace 1 over 9 with that value. And then once again, you will do this simple calculation of multiplying your k inverse with your ciphertext, and you should get back your plain text. Karavardina, you have a question?
Yeah, I might have missed this, but did you say we will need to know how to do the decryption as well for the exam?
Yeah, both encryption and decryption, but only for a 2x2 matrix, not for a 3x3 matrix.
Okay, thank you.
Okay, so this is all with respect to our basic symmetric algorithm, and which is for the this specific class that I wanted to cover. But I also wanted to cover one specific example, which is the first standard. Let me tell you one thing. 1 second. I'm trying to find um, the slide. 1 second. Okay, this one. This particular slide I will be posting in the next week, but I wanted to cover one specific thing over here that so far, if you remember, we have covered a lot of algorithms, symmetric algorithm, symmetric encryption algorithm. We cover ROT 13, ROT 13, where you have to add 13 character, Wigner cipher, Wurman cipher. We also did Caesar cipher, which is a kind of a shift cipher where you add +3. Under transposition, we did cover transposition cipher, Colminer cipher, rail-fence cipher. And under block cipher technique, we cover Playfair cipher and Hill cipher technique. The other important things which are important in symmetric algorithm are these two standards, which is DES and AES, data encryption standard and advanced encryption standard. And they also process block of characters together, 2 characters, 3 characters, bulk of characters together. And that is the reason it comes under block cipher technique. And these are standards which our industry generally do follow. But before I go in terms of making you understand the standard, the very important thing is for you to understand the standard is your Feistel cipher structure. So this is a Feistel cipher structure, which is also very important. And I believe in your quiz and in your final exam, I will give you one question on this Feistel cipher structure. So what exactly this Feistel cipher structure means is that you take your plain text block and whatever is the size that you want to process it, you will divide it into 2 parts. So generally, what happens is, let's suppose you have 64 bits together, or 64 is your block size. In the previous example, I was covering just two characters together. So you were processing just 2 blocks of character, 2 characters together. But the standards, which are DES and AES standards, they can process even larger size. And these sizes are varied between 64-bit, 128-bit, and so on. So Feistel cipher structure is a kind of a structure which basically process a larger bit size. And what exactly it does is that, let's suppose you have 64-bit of data. So what it does is it will first divide your 64-bit of data to your 32 and 32. So it will divide that 64 into 2 parts, which is, or maybe let me give you 8-bit of data. Let's say 8-bit data that you want to process. So you will have on your left-hand side 4-bit and your right-hand side your 4-bit. Then what you do is you take your right-hand side bit of data, which is 4-bit, you apply a Feistel function, which is f which will take in the key that you are using, which is K1, and you will do some kind of computation over here, which is with respect to write bits. So your key and your write bit should be 4 bits so that you can perform this function. This resultant that you will get after processing your right hand side bit of data using the key K will be XORed with your left hand side of data, and whatever is the resultant, which would be a 4 bit of data, will now become the new write bit. And whatever is the previous write becomes the new left hand side. So I'll show that in the whiteboard as well, so that you guys understand. So what exactly happens in this Feistel cipher structure is you start with um, some bits of data. And let us imagine you have 8 bits of data. What you do is you divide it into 2 parts, and you will make it as left hand side and right hand side. So you will have 4 bits over here and 4 bits over here. You will take key, which is generally termed as a round key. And this round key should be of the same size of this half bits of data that you are processing. So let's suppose your round key is also 4 bits. So what you will do is you will perform some simple calculation. So let's suppose your data was 0001 and 1101. I'm just giving you a random example. So you had your original 8-bit data as 0001, 1101. You will divide it into 2 parts, which is your first 4 bits become the left hand side and the last 4 bits become your right hand side. You will also take some key, which for instance, your key is 0, 0, 0 and 0. I'm just giving a simple example. All the bits are 0. So you will perform one function on this right hand bit side, and let us suppose we perform an AND operation, which is 0, 0, 0, 0 and the right hand side. So AND operation will result this 1 and 0 is 0, 0 and 0 is 0, 1 and 0, 1 and 0 is 0. You will XOR this resultant with the left hand side. So if you remember, XOR operation will always give you a 1 when the bits are opposite. So 0, 0, 0, 1, which is your this, and 0, 0, 0, which was the resultant that you are getting, the output would be 0, 0, 0, 1. So this output that you are getting will now become the right hand side, so which is 0, 0, 0, 1. And your previous right hand side, which was 1, 1, 0, 1, will become your left hand side, which is 1, 1, 0, 1. Once again, and this is just round 1. So this thing that you did is round 1. You will again process these bits together. So what you will do is, once again, I'm taking the key as 0, 0, 0. So you will do an AND operation on this, which is 0, 0, 0, 0. The resultant would be 0, 0, 0. You will XOR with this output, which will XOR with 0, 0, 0, 0, which will give you 1, 0, 1, 1. This resultant will now become the right hand side, and the previous right hand side, which was this value, becomes the new left hand side, which is 0, 0, 1 and 1, 1, 0, 1. And this corresponds to the second round. Is it making sense what exactly happened over here in Feistel cipher structure?
Yes, ma'am.
Okay, so both your data encryption standard and your advanced encryption standard are based on this kind of structure, where you shuffle the bits, you rearrange the bits, you divide the bits, you perform some computation, make the previous right hand side the new left hand side, the previous left hand side the new left hand side, and so on. So it does all of this, and that is the underlying principle for your uh, Feistel cipher structure, which is the underlying principle for your data encryption standard or advanced encryption standard. Okay. I have in your exam, what I will be doing is I will be giving you question like this. What I will be doing is, and I think your quiz also has that specific question example. So what I'll give you is I will give you the ciphertext. So this is the ciphertext that you are getting. So I will give you the ciphertext and I will ask you to get the plain text. And I'll give you what exactly is the function used, and you have to solve in order to get back the plain text. That would be a question that I will be giving it to you, so that you know how to reverse process the certain examples in order to compute the value. I can do one specific example if you want. Um, let's do one example. Maybe that would help you. Okay, so the example is your key has K1 and K2. So K1 corresponds to 1100 and your key 2 is 1010. And I want you to solve for the plain text, which is 10100101. And the operation that you would have to do, that function, that Feistel function that you have to do is an AND operation. And tell me the ciphertext that you are getting by solving this. So solve it. I am also solving it. You also solve it and tell me what would be the output that you are getting and versus what I'm getting. So do you even understand the question, what exactly the question is? You have to process two rounds of operation, two rounds of operation. In the first round, the key is 1100. In the second round, the key is 1010. The Feistel function that you have to apply is AND operation. So follow similar thing, which is in this particular diagram, where you take your right hand side, perform key times your right bits and your key, do the AND operation, the resultant you will XOR with the left hand side, and that becomes the new round. Okay, so solve it. Does it make sense? Any question in terms of understanding the question itself? Please solve it, because that would help you to even do one of your quiz question and in your final exam as well. This would help you.
So you take the first key and in the right side, and
Mm-hmm.
you use the AND operation there,
Yeah, yeah,
and then you XOR with the left side.
yes.
Okay, awesome. Thank you.
Please write down in the chat whatever is the output that you are getting after doing these two round of operations to get your final ciphertext. And then, so the AND operation is 0, 1, 0, 0, correct? And XORing with the left-hand side. No, why is it giving you 0, 0,
Oh, I
0?
did and again. I'm silly. It should actually be
So Daria, you are right. Your left-hand side. Wait a second. Your right-hand side. Hmm? Are you sure that you are getting 111 right-hand side as 1010? So you XOR 1010 with your 0100. Yes. Yes. So Mitch, you are right. It is left-hand side is 0101 and right-hand side is 1110. So let me solve this, the very first one, and then so what we are doing is, first of all, your bits are 1010 and 0101. So this is your right hand side and this is your left hand side. So here in this case, I'm taking the first key, which is 1100, which is 1100, and I'm doing an AND operation. So this is 10 is 0, 00 is 0, 11 is 1, and 01 is 0. I will take this output and I will XOR with my left hand side. So the resultant would be 1 and 0 will give me 1, 0 and 1 will give me 1, 1, 0 will give me 1, and my last one, 0, 0 will give me 0, 0. So now this side, which I got, becomes the right hand side. So this is 1, 1, 1, 0. And my previous right hand side becomes the new left hand side. So this will come over here. So this becomes 0, 1, 0, 1. And now once again, we'll do the same operation, but using the key, which is 1010. So again, I'll take 1110. I will AND with 1010. So this would be 0. This would be 1. This would be 0. This would be 1. You will XOR with this. So the output would be 0, 1 would be 1. 1, 0 would be 1. 0, 1 would be 1. 1, 0 would be 1. Which means now this becomes my right hand side, which is 1, 1, 1. And my previous left hand side was this, which is 1, 1, 1, 0. Is everyone getting that? This out?
yes. Actually, seeing you go through it made it a lot clearer.
Awesome. So that's one of the example, and I think in your quiz I have given you this kind of a question where the function would be something else. The function will not be an AND operation, but it could be some other operation. But you should know how exactly you switch the bits together in order to get the final output. Any questions with this? Was it too much for the class today, or do you want me to now cover the next topic, or you guys are good and you want to? I'll cover the standards maybe in the next class. But if you want, I can cover the standards today itself, like the first standard I can uh, explain. So yeah, K1 in round 1 and K2 in round 2, yes. Yes, I will publish this on Canvas. So how do you guys feel? Should I start with data encryption standard, or you are good for the class today? And I'll cover the standards in the next class on Wednesday when we will meet in person.
Can we start?
You can start? Okay, awesome.
Sure.
Okay. So data encryption standard is block cipher technique, and it can process 64-bit of plain text together. And here 16 rounds are done. In the previous Feistel cipher structure that I was explaining it to you, they were just like some kind of rounds. But here in the data encryption standard, the way it is processed is that we take 16 rounds and we have 64 bits. The key size is 64-bit. We create 16 keys. In every round, a new key is generated using some kind of an operation, which I'll cover. And then from the 64-bit key, you basically create a sub key, which is 48 keys. And I'll tell you what exactly is the process, but the output you get is a 64-bit output. So data encryption standard, first of all, is a block cipher technique which can process 64 bits together. Hill cipher was able to process 2 characters together. Playfair, 2 characters together. This one can process 64 bits together. And how exactly it does is very similar to Feistel cipher structure. So as I explained you, Feistel cipher structure is you take your plain text, which is 64-bit. Initially, you do some kind of initial permutation. And based on that initial permutation, you divide them into 2 parts, which would be 32 bits and 32 bits. You will take your 32 bits data, you will apply your 64-bit of key using the Feistel function. Then you will process your left-hand side with the output of that in order to get the right-hand side, and the previous right-hand side becomes the new left-hand side. And this is round 1. In round 2, once again, you will take your right-hand side, have another 64-bit keys, which you start from this, but you change certain bits value. So you get another 64-bit. Generally, it is same. Sometimes it is changing. And I'll tell you, it is round specific. Sometimes they use the same round key in every round, and sometimes they change a single bit. But in the second round, once again, what you do is you take your 64-bit key, you take your right-hand side, apply a function, and your previous left-hand side, you will XOR it to get your right-hand side, and the previous right-hand side becomes your left-hand side. Very similar to your Feistel cipher structure that we were covering. That is round number 2. In round number 3, once again, the same process happens. In round number 4, once again, it happens. Then round 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total 16 rounds are done. And finally, you do a final permutation, and finally you get your 64-bit of ciphertext. So you start with your 64-bit of data, and you get an output which is also 64-bit of ciphertext. And the way you do is, following a Feistel cipher structure. And this time the Feistel cipher structure is much, much more complex in comparison to the previous example that I covered. But I'll go step by step so that you understand. So first of all, what is permutation? There are three kinds of permutations in data encryption standard. One is a simple permutation where you change the bit order. So for instance, if your bit is 1, 2, 3, and 4, so the first bit will go to third bit. So this will come over here. This bit will come over here. The second bit will come on the first position. The third bit comes on the second position. The fourth bit will remain fourth bit. It's a simple permutation. You just swaps certain positions in order to generate a new bit output. Expansion permutation is when you expand the number of bits. So you start with 4 bits. So here it is 1, 2, 3, and 4. And you expand it to a larger set. So 4 bit, you expand it to maybe 6 bit. So how exactly you expand is you take the first bit and you put the first bit as is. You take the second bit and you copy that second bit to your, and this is all random. It's not fixed. What I'm showcasing you is just random. It's just for the illustration purposes so that you understand what exactly happens. So in this, you take the second bit and you copy at the second position and the fourth position. You take the third bit and you put this in the fifth position. You take your fourth bit and you put this at the third position and your last position. So in the end, you are expanding from a 4-bit value to a 6-bit value. That is expansion permutation, expanding the number of characters. Permutation was just swapping the different position. And permutated choice is minimizing. So you start with 4-bit, which is 1, 2, 3, and 4, and you put this into 2 bits. That is permutated choice, starting from a larger bit values and making it in a smaller character set. So here, 1 will not be copied, fourth will not be copied, second goes to the second position, and third goes to the first position. So in the end, from your 4-bit output, you are getting a 2-bit output. So that is permutated choice. And these are the 3 different kinds of permutations which are being used in data encryption standard. So you switch certain positions, then it becomes permutation. When you start from a lower bit values and you expand it to larger one, that is termed as expansion permutation. When you start with the larger bit values and you make it into smaller bit size, then it becomes permutated choice. So that is what is termed over here, which is initial permutation and your final permutation. And there is in between permutated choice as well. So in initial permutation, which is the first round of block, what happens is you start with the 64-bit plain text, and which is all random bit of data. So let's suppose you take your first 64-bit, the very first operation is you switch certain position, and that is termed as the initial permutation. So what you do is first bit goes to 40th position, second bit goes to 8th, third bit goes to 48, fourth bit goes to 16, fifth bit goes to 56, next bit goes to 24, then 64 and 32. So you are just swapping positions. So 64-bit value, but you are swapping different position. That is initial permutation. And this permutation, which is final permutation, is also swapping different positions. So these are the initial and the final operations which are done on data encryption standard when you start your 64-bit of data processing. You start with 64-bit data, perform an initial permutation where you swap different position, change certain position. That is initial permutation. And once you process all the 16 rounds together, once again, you do a final permutation where again you change the different position values. And that is basically the first permutation that you do and the end permutation that you do. I think I will go with the next step maybe in the next class so that you guys understand. But for this class, I believe you should have a good understanding in the data encryption standard processes 64-bit of data, has 16 rounds, has 16 keys, and the key size starts with 64-bit key. That's all I want you to remember. In the next class, I'll cover how exactly this DES and after that, how exactly the AES works. And these are the industry standards which are being used in most of the industry. Most of the industries do use this DES and AES, and we should understand why exactly we are doing all of this and what is the underlying mathematical operations which actually happens. Okay, with this, I believe if you have any questions, I can answer this. If no questions, feel free to leave the call and we'll meet on Wednesday.
Dr. Rodor, are you going to have office hours today?
Not today, but I can meet with you if you want right now for like 10 minutes. I have a meeting at 2, but if there's something I can answer.
Not really, not off the top of my head. If anything, I'll probably just come up with an email or something.